Okay, hey, advanced chemistry, good morning. Yesterday we were talking about some colligative properties and discussing some vapor pressure and vapor pressure depression and freezing point and melting point and boiling point, and we drew some graphs and life is good. And we got to about here and we didn't get a chance to talk about the mathematical relationship, which we're going to do today. So here we go. The change in boiling point or freezing point, which yesterday we symbolized as change in boiling point as delta T sub B, so change in the boiling point. And freezing point we symbolized as change in T sub F. And remember, the boiling point was always elevated because of the relationship in that graph of vapor pressure versus temperature we were looking at. And the freezing point is always going to be depressed or lowered. And the change can be determined by this. Delta T of either F or B is equal to a K value. And we're going to come across K values quite a bit. And this K is a constant, and it's going to be K sub F or K sub B. We'll talk about that more in a second. Times the concentration of the solute times the Van't Hoff factor that we were discussing yesterday. So we know what delta T sub F or B is. Let's talk a little bit more about these. So right now, let's just name K. This K sub F or K sub B is called the molal freezing or boiling constant. The molal freezing or boiling constant. And we're going to talk about that more here in a second. By the way, the molal freezing or boiling constant is for the solvent, so we'll say of the solvent. So whether that be water or some other solvent that you're using. Small m is the molality. Remember molality of the solute. So the concentration of the solute in molality. And then, of course, I is that Van't Hoff factor that we were discussing yesterday. One thing that gets confusing about this equation is what applies to what part of the solution. So if you think of this equation as kind of being split in half here, everything on the left side has to do with your solvent. Everything on your right side has to do with your solute. So the change in temperature is the change in the freezing point or the boiling point of the solvent, and then the K is that constant for the solvent. The molality and the Van't Hoff factor refer to the solute. So always the left-hand side is your solvent, and the right-hand side is your solute. Let's talk a little bit more about this K value. KF and KB. The freezing point and the boiling point of a solution with a solute in it, we're going to be able to find that if we have these KF and KB values. And remember, that is called the molal, the molal freezing, well, that's not right. The molal freezing constant or the molal boiling constant. And really, there's more to these names. The molal freezing is the molal freezing point depression constant, and it's the molal boiling point elevation constant. But sometimes we just leave that out and call them molal freezing or molal boiling. So these are intensive physical properties. Remember, intensive physical property means does not depend on, I'm struggling spelling today, does not depend on the size of the sample. So no matter how much water you have, its molal freezing constant is always going to be the same value. The units of these constants are kind of interesting. They're in degrees C per molal. And what that does for us, well, is a couple of things really. This unit tells us how many degrees change per 1 molal of solute. And I have asked your substitute to give you a reference sheet here. And so you can see some different examples of those solvents KFs and KBs. So for example, water's KB is 0.512 degrees C per molal. So if you have 1 molal of solute, then that is going to increase the boiling point by 0.512 degrees Celsius. If you compare that to like carbon tetrachloride, different solvent, that is going to be influenced more by 1 molal of solute, increasing the boiling point by 5.03 degrees per molal. These are also in your book on page 502 and 500 if you're interested, but you have that handy dandy reference sheet. So let's apply this concept to some examples. So here's our first example. I'll let you write it down. It says 112.0 grams of potassium iodide, Ki, is dissolved in 90 milliliters of water. What will the freezing point of the solution be? So our solvent is water, our solute is potassium iodide. We need to know the freezing point of the new solution, and we have this relationship here. Change in the temperature of the freezing point is equal to the molal freezing constant times the molality of our solute times the Van Hoff factor. So let's see what we know here. This 112 grams of potassium iodide dissolved in 90 milliliters of water is to help us decide our molality. So let's do that first. The molality of my Ki, remember, that is the number of moles of solute divided by kilograms of solvent. So for moles of Ki, I have 112.0 grams, and the molar mass of potassium iodide is 166.0 grams per mole. So 112 divided by 166 gives me 0.6747. 4 sig figs each. So if I take 0.6747 moles and kilograms of water is 1 gram per milliliter, so I divide 90 by 1,000, I'm going to have 0.0900. So if I divide 0.6747 by 0.09, 3 sig figs gives me 7.50. Molal. So I know my molality of the solution. Let's do I next. It's Ki. So if this is fully dissolved, I should have K plus 1 and I minus 1, which would give me a Van Hoff factor of 2. Kf. Remember, if I divide this equation in half, everything on the left side has to do with my solvent. So over here on the right side, I was dealing with the Ki, its molality, and its Van Hoff factor. Now I'm switching over to water. So the Kf value for water, if I look at my reference sheet, Water's KF is 1.86 degrees Celsius per molal. So now I have everything I need to figure out the change in temperature of my freezing point. So if you look at units here, molality on the bottom and here on the top is going to cancel. So my units are going to be degrees Celsius, which makes sense for a change in temperature. And I'm going to multiply 1.86 times 7.5 and times 2. I'm going to get 27.9, and that's good to have 3 sig figs. This I value right here really has an infinite number of sig figs because it's not measured. I'm going to have exactly 1,2 moles of particles per solution. So this is not factored into sig figs in case you're wondering. So I have 3 sig figs here in this measured value. I have 3 sig figs in this measured value, so I should have 3 in my answer. So I know that water does not freeze at 27.9 degrees Celsius, but what I do know is that this is how much it is depressed from its normal value. So the new freezing point is going to be its normal freezing point, which is 0 degrees Celsius, and it's going to go down 27.9 degrees Celsius. So now the solution is going to freeze at negative 27.9 degrees Celsius. So we need that original, what was that original freezing point value, because it's going to go down from there. Okay, let's do another. It says, suppose 24.3 grams of carbon disulfide is dissolved in 128.3 grams of carbon tetrachloride. What will the boiling point of this solution be? Okay, so let's set up our relationship here again. I'm going to have delta T sub B this time, Kb molality times the Van Hoff factor. So again, let's start with our solute pieces over here and figure out the molality of our solute. So I've got 24.3 grams of carbon disulfide, and it's dissolved in this many grams of solvent, which is carbon tetrachloride. So let's find first, I'm going to have moles of carbon disulfide divided by kilograms of carbon tetrachloride. So the number of moles of CS2 would be 24.3 grams, and the molar mass of carbon disulfide is 32.07 times 2 plus 12.01. That gives me 76.15 grams per mole. And if I have 24.3 grams, that gives me 0.319 moles. Okay, I have the grams already of carbon tetrachloride, so I'm just dividing by 1,000 there. 0.128 kilograms. Oh, 0.1283 kilograms, excuse me. Still 3 sig figs there, 0.319 divided by 0.1283. That gives me 2.49 molal. I'm going to go ahead and plug that in, 2.49 molal. My Van Hoff factor, this is a covalent compound, so it is non-ionic, it is non-electrolytic, because it does not dissociate. For every 1 mole of carbon disulfide, I'm going to have 1 mole of particles, so my I factor is 1. Not ionic, covalent. I know that because of 2 nonmetals. I know that because of a prefix. Van Hoff factor is 1. So the only other thing I need, and remember, for my solvent, I need my molal boiling constant. So if I look at my reference sheet for carbon tetrachloride, that value is 5.03 degrees C per molal. So again, molality cancels, so my change in boiling point is going to be 5.03 times 2.49. 3 sig figs gives me 12.5 degrees Celsius. Now that's the change in the boiling point, so the new boiling point is going to be equal to the original boiling point of carbon tetrachloride, and that's going to go up by 12.5 degrees Celsius. So for carbon tetrachloride, the boiling point is 76.7 degrees Celsius normally. add to that 12.5, and we get the new boiling point of 89.2 degrees Celsius. So for your assignment, I would like for you to try all of the colligative properties practice problems, 1.5, except for I will have you go ahead and skip number 5 and number 6. And I will see you tomorrow. Have a great day.